So thank you all for staying for my session today. I'm going to talk to you about the flexibility and the performance of our quantum platforms. This talk is actually going to dovetail nicely with what Jonathan was just talking about. We're going to go a little bit higher up in the stack, talking about how those kind of concepts connect to applications, and go a little bit lower in the stack, talking about how that connects to hardware. But spend a lot of time in the middle too, covering some of the same territory, giving you our perspective on many of those same concepts. So let me just talk about defining performance, about what I mean when we're talking about performance of quantum systems. We really think of quantum performance as having three critical factors: the scale, or the number of qubits; the quality, the size of the quantum circuits you can execute without too many errors; and speed, which is kind of the amount of quantum work you can do per unit time. We have metrics up on the screen to measure each one of these. In particular, for quality, we introduced several years ago a metric known as quantum volume, which has now been increasingly adopted throughout the industry. And speed, as Jonathan was just describing, we've recently introduced a new measure for speed, which is known as circuit layer operations per second, or CLOPS. And I'll spend some more time talking about CLOPS in a little bit. So scale and quality, you're going to hear more about in the talk of my colleague Jerry Chow tomorrow in his session on Wednesday. But I just want to touch on a few little pieces of news and progress on these two factors, just to kind of put together an entire story. So on scale, a little over a year ago, we published a roadmap of quantum hardware, and our plans to build a new generation of quantum hardware every year. Just a few weeks ago, we announced the success of being able to put together the next step in that roadmap, which is the Eagle processor, a 127 qubit platform, which I can say is the most advanced superconducting processor ever built. And it takes advantage of IBM's deep expertise in CMOS technology to integrate a new wiring technology to solve some routing and I/O problems in quantum processors while preserving the performance of the chip. So the Eagle has landed. These devices are in fridges now, getting brought up. This is a heat map of some of the characteristics of the IBM Washington processor, which the team is busily preparing for customer use and client use by the end of the year. And again, Jerry will tell you more about this device in the session tomorrow. On quality, we've also made a number of advances in the past year. In fact, in the past year, we've made two steps in quantum volume. The highest quantum volumes we've been able to demonstrate at IBM, showing quantum volume 64 and then 128 in the same year. Quantum volume is a holistic benchmark. It kind of puts everything in that impacts quality and requires you to demonstrate it all at the same time, rather than demonstrating individual pieces in isolation. But we have great optimism that we're going to be able to continue to drive improvements in quantum volume because we're making advances in those fundamentals as well. So I want to tell you a little bit of news about some of those fundamentals. In particular, our team has made significant progress on coherence and gates. On the coherence side, our Falcon R8 processors are showing 3x better T1 times than the prior generation Falcon R5 processor, moving us from 100 microsecond average T1 to 300 microsecond average T1. And we have test devices that exhibit even better performance, an average T1 of over 600 microseconds, showing us that there is, in fact, room to continue to push on the same kind of ideas that have led to the Falcon R8 improvement. Furthermore, we've been able to translate that excess coherence into gate performance. You can see on the right-hand side a plot of error rates, 2-qubit error rates on IBM processors as over time, as well as against processor family in the color code. And you can see that the team has been able to continuously drive down 2-qubit error rates, which is our dominant error on these devices, year on year. And in fact, just recently broken through the 3 nines gate fidelity barrier with an exploratory Falcon R10 system that is just below 1 times 10⁻³ error. So there's lots of room for continued drive on scale and on quality. Speed is a tricky thing to define in this era of quantum computing. The principal problem is like the most of your strategies you're familiar with for making a benchmark for speed in classical computing have to contend with the fact that our quantum systems today produce errors, right? So if you want to say that your quantum system does a particular task in a certain amount of time, how often does it have to get the answer right in order for you to say that that was a valid benchmark? And this is just one of many, a myriad set of sort of complications in trying to define speed for quantum processors. Another example is that quantum hardware today doesn't have sort of a heartbeat, a clock that is consistent for every instruction. It's like having instructions in a classical processor that some of them take 1 clock cycle to execute and some of them take 500 clock cycles to execute. So what is your effective clock rate? So you have a kind of a minefield to navigate in trying to define a speed benchmark. But it's important to try to get some kind of handle on speed, because speed brings practicality to quantum computing. What I mean by this is most workloads that we are interested in are not workloads that involve execution of a single quantum circuit, but in fact, execution of large families of quantum circuits. Our applications research team routinely encounters tasks requiring executions of hundreds of millions, if not billions, of circuits. And so speed can be the difference between one of those tasks being something that would take months to execute once to being something that can be executed in a few hours. And so speed is a critical benchmark that we get a handle on measuring it in a platform agnostic way. So we can compare different system kinds and then use that as a tool to sort of to drive our own improvements in performance from a speed perspective. So as Jonathan mentioned, we've recently put together our best effort at navigating this minefield of speed with a new benchmark called circuit layer operations per second, or CLOPS. We posted this as a white paper on the archive and have invited comment from the community to help us refine this benchmark and make sure that it can withstand the test of time. We've also begun measuring it on our systems, though. On our systems today, we can achieve CLOPS of about 1,400. We've also gone back in time trying to infer the performance that we think we had a few years ago. We think a few years ago we were down at about 200 CLOPS. We've also tried to infer what the performance might be of other systems. So, for instance, we looked at some ion trap technology where the kind of the fundamental ingredients that they're working with may put an upper bound on the performance of those systems that's substantially less. And if you did a similar kind of analysis of just like, what if you were just limited by the gates on your hardware, our own superconducting technology would admit the possibility of a CLOPS of 200,000. So you can see there's a massive gap between where we are today and where we can go. And we really think one of the fundamental advantages of the superconducting platform is that it is capable of innately fast speeds. But it also, by doing this task, reveals some of the gap of where we have to go, right? So when we started running the CLOPS benchmark in our own systems, that revealed to us that the actual time of executing the circuit was only 3% of the wall clock time for this CLOPS benchmark. So you can see that there's a lot of room for improvement, and we will be very much focused on driving that number up over the coming year. So how do we get from the 200 CLOPS to 1,400 CLOPS, and how we're going to continue to do better? It involves pieces up and down the stack. So it involves things like control electronics. So we're benefiting now from a second generation of control system, which among several other improvements also has much faster program loading times. We have improvements at the bottom end of the stack, which is the quantum hardware itself, changes to the design of the quantum chips to admit faster measurement instructions, which was one of the slowest instructions on our systems. You can see that we've, from the Falcon R4 processor to the Falcon R5, made a substantial improvement going from about a 6 microsecond measurement instruction duration down to well below 1 microsecond. The R5 has an average of I think just under 700 nanoseconds for the measurement instruction duration. But that's not enough, because real applications are not just at the quantum layer, but they involve interactions between quantum and classical components. And so as part of the CLOPS benchmark, we built in this structure to it that you had to execute mini quantum circuits influenced by classical computation. If you look at these kind of interactions, though, you'll notice that they come in different flavors. Not all quantum classical interactions are the same. And we like to actually think of them as coming in two different time scales, two different relevant time scales. There's the real-time interaction, which is the interactions necessary for things like teleportation, for things like heralded state preparation, right? Which is this demanding latency domain where I need that data within a few hundred nanoseconds or microseconds. But the domain which is really relevant to a broader class of applications is the near-time classical domain, which is not quite as stringent in the requirement for latency, for the demand for latency, but really needs a completely generic compute facility, as generic as you can give, as you can deliver. So I'm going to focus now then on our strategy for accelerating that near-time classical domain. And in order to do it, we had to really rebuild our architecture from one that going from the old model, which was one that a user submitted circuits for execution, to one that now a user submits a program, and we execute that program on container infrastructure, which has low latency access to our quantum hardware. And that structure allows for really the execution of generic code, but in one which doesn't have to wait for a long trip back over the internet to the user or wait for another pause in a queuing system. So we built this system earlier this year and launched it as a beta in May at our IBM Research Think event. And we were able to put together all these different components I've talked about and some that I haven't to demonstrate a massive speed increase on a real application. So what we did was we looked at the lithium hydride molecule and the variational quantum eigensolver, effectively revisiting work that we had done a few years ago, and show that we could do the same calculation 120-fold faster using the Qiskit runtime and these other technologies. You can see the effect of the Qiskit runtime on its own in the chart on the right-hand side, which shows you the trip times for one step in one iteration in the optimization loop, which is the inner loop of the variational quantum eigensolver, showing that we're taking from the circuit model, which is a 2-minute trip time on average, down to about a 20-minute trip time with the Qiskit runtime. And there's substantial room to make that even faster. So the Qiskit runtime launched as in a beta in May. As of October, the Qiskit runtime is available on all of our systems, and our premium users can upload and execute their own programs. Our next step is to make the Qiskit runtime available with tighter integration with IBM Cloud accounts, so that users can use the Qiskit runtime with other IBM Cloud technology. I'm going to return to that in a few minutes. So we talked about performance as being scale, quality, and speed. But we think that to actually get value out of quantum hardware, we need some other ingredients too. In particular, we need to couple that performance with advanced capabilities. And by that I mean things like error mitigation or circuit knitting that allow us to do more with the quantum hardware we have now. We also need to deliver that in an experience which is easy to consume and deliver, meaning which is a concept we talk about as frictionless computing. And so let me now turn to these ideas of capabilities and frictionless to tell you a little bit about where we're going next. So perhaps the easiest way to explain capabilities is with an example. So I mentioned this word circuit knitting. We can dig into what is that. Circuit knitting is a technique which allows the execution or the solving of larger problems by taking a quantum circuit and breaking it or cutting it into smaller circuits. This is a strategy that works in general, but at exponential cost. But there are certain cases where you can do it, where you can take advantage of a symmetry of the problem, where the reassembly and post-processing can be done efficiently. And so our team in the past year used a variant of circuit knitting, something known as Entanglement Forging, which takes advantage of weakly coupled links in your quantum circuit as natural cut points, where then the reassembly can be done with polynomial cost. And we did that, we used that to do a simulation of a water molecule with a collection of 5-qubit circuits. But we're able to do that simulation, which would have required very large circuits otherwise, and break them down into these smaller, easier to handle components. And as a benefit, you also get a more accurate simulation too. These capabilities often have an interaction with those performance metrics of scale, quality, and speed. In particular, each one of these capabilities usually involves some sort of trade. And for that reason, it's actually important that we have an excess of capacity in one of these measures, whether it's scale, quality, or speed, so we can trade them against each other. The circuit knitting technique, in particular, trades off speed, because I need to run more circuits, for a boost in the size of the problem I can tackle, so a boost in scale, and a boost in quality or accuracy of the result. All right, so I'm going to trade off speed for improvements in scale and quality. Let's look at some other capabilities. There's another example. It was something called quantum embedding, which takes your problem and splits it apart into a part that you're going to tackle with classical resources, with classical approximate methods, and a part that you're going to tackle with quantum methods. An example might be if you have a molecule that is split into an active and inactive space. You might use something like density functional theory, which is an approximate method to simulate the inactive space, and use quantum techniques to simulate the active space, and then stitch those together. This is a technique which has a different scale, quality, speed trade-off in the sense that we're, by embedding the quantum within an approximate classical method, we're sacrificing a bit of accuracy, but for, again, a benefit of being able to tackle a larger problem, larger scale, and have it execute faster. Other capabilities you're maybe more familiar with in the past are things like error mitigation, which uses collections of circuits to get more accurate estimates of observables, has a similar trade space to circuit knitting, or error correction, which of course embeds information in redundancy of encoding in physical qubits to get a boost in quality by sacrificing or trading off against scale and speed. So all this family of advanced capabilities all have something in common, which is that all of them involve combinations of quantum and classical resources that are coming together to do more than what you could do otherwise. And it's for this reason that we really think of delivering this capability of making quantum plus classical mixtures is a very powerful concept, right? Because it can reduce the depth of the circuits you have to execute, it can reduce the width, the number of qubits required, and it can improve the accuracy of the result. So in short, we think that quantum plus classical as a capability, as a technology, is going to be critical to accelerating delivery of quantum advantage on a variety of use cases. Now let's turn to frictionless. So these capabilities all sound great in practice, but in order to actually take advantage of them, we need them to be easy to use, easy to consume. And we need to be doing everything we can to sort of get the advanced technology kind of out of the way of the developer to make it as transparent and easy to use as possible. There's a number of things where the way we build our systems introduce interference for the user. One of the things that we've heard about from our users is that they would like other ways to access our hardware, our quantum systems, and be able to use that in concert with other cloud technologies. So to address that, we will be offering a new way to access IBM quantum hardware, new IBM quantum systems, directly integrated with IBM Cloud accounts. This will allow you to create collections of services that have classical resources and quantum resources, potentially accessing serverless HPC-like infrastructure and other cloud technologies like GPU clusters and so on. And also will deliver a different payment model where you can do pay-as-you-go as opposed to contractual queue slots. The way that this will look is like using any other cloud service. You basically create an instance, connect that with a plan, and then you're ready to execute against that service that you've spun up. Our timeline for launching this is that we're going to have a limited beta release in January, where there will be just a free plan, and 2 IBM quantum systems will be attached to the service. This is effectively where we enter a feedback phase to collect. We get users start using it and tell us what they think, how we might improve the experience, aiming towards a full beta release in March, where we now turn on the pay-as-you-go model. And then from March onwards, we'll start adding systems to this access model. In the summer, we'll start to think about ways to transition, to give the option to transition customers from the Q-slot model to cloud credits, if this is their preference for how to access our systems. And we'll start to introduce other systems, not just our core systems, but exploratory systems as well, so that users can access the best of IBM hardware however they like. Another aspect of Frictionless where we believe our systems are getting in the way of our users, as we think about these more advanced capabilities, is that we imagine a day where a user wants to build an application, a quantum application, which takes advantage of a variety of technology, right? You have your application where maybe some component is purely classical but wants to use a GPU cluster. You have another function that actually runs on quantum hardware. It has some post-processing step that maybe needs to use some more classical compute, and so on and so forth. How are users going to build applications like this? As we started to think about what a developer needs in order to build an application that has collections of different kinds of compute resources, we think of a few requirements that are out of what this should look like. In particular, most of our developers are Python developers, and so we want it to be sort of intuitive to a Python developer. It should have low barrier to entry. It should be pretty simple to specify what kind of resources you need for each part of the computation, by just specifying the compute architecture, the amount of memory it needs. But we really want to deliver a serverless experience where the developer is focusing on writing code and not focusing on infrastructure setup or scale. And so we've put together a demonstration that we believe has these characteristics, taking advantage of lithops, which is a Python framework, and IBM Cloud Code Engine as an orchestration technology to deliver this kind of experience. So the architecture of our demo looks like what you see on the screen here, where we have the Qiskit runtime on the bottom, but now it has IBM Cloud Code Engine as an orchestration layer in front. And Code Engine can now effectively orchestrate the use of scalable classical resources with quantum resources and make them the connections back and forth between them. So you can think of how this would work in the circuit knitting capability you were talking about before. You can think of an example, an application where maybe a user submits an application. Maybe I don't know automatically where the right place is to cut it. Maybe I need to do some computation to figure out where the best cuts, most advantageous cuts would be. And maybe that is a hard classical computing task. But I can distribute that out to some scalable classical resources. Once I've figured out what those smaller circuits are, I could then send them off to quantum hardware using the Qiskit runtime to enable that. And then send it back to classical resources to do the reassembly, the post-processing at the end. So that's the kind of concept that we have for how this might work. We've actually put together a smaller example, a real example, using the variational quantum eigensolver, but now running it on Code Engine, where with just a few lines of code, we can basically stand up this kind of system where Code Engine will instantiate some classical nodes. It will distribute the calls to execute circuits to the Qiskit runtime. That data comes back to Code Engine, and this sort of infrastructure allows for monitoring or progress reporting while the system is running, which is what it will show next. And then when it's finally done, the user can get it back just as if they run it on a local simulator. But instead now it's all been orchestrated seamlessly in the cloud. And so this is actually what real data looks like coming out of this kind of system, again, for basically the one iteration for one configuration of I think in this case is the hydrogen molecule. So while we have the notices from our lawyers, I just want to wrap up. If there's just two things that you can come away from today, is really just two concepts. One is which we believe that advanced capabilities, which have these trades, performance trades between scale, quality, and speed, are going to be critical to achieving quantum advantage sooner. And the second is that we at IBM are committed to making these advanced capabilities easy to use in a frictionless experience. So thank you for your time. Questions?
Hello, thank you very much for your presentation. So I like one of your slides where you showed that a GPU and also like the QPU and the other CPU. Can you go back to that slide?
Sure.
Just want to. Yeah, this one. Mm-hmm. So previously, like so normally we use this general purpose like a computer architecture as a CPU software, right? So recently, like especially when we have deep learning, we have more and more like domain-specific architecture as GPU or like FPGA acceleration for some, for example, for DNA, right? Do you think in the future, so the entire computer architecture will be just a combination of different domain-specific architecture like CPU, GPU, QPU, and quantum computing is just a subset of the entire architecture that does some part of the job. For example, for optimization, for cybersecurity, for example. Do you think that's something in the future? I write a program and I let this part of the program to be computed in like a quantum program, just like this.
Sure. So I definitely think that particularly for the near future, quantum computers will exist in an accelerator model, right? They're not good at all tasks, they're good at some tasks. You're going to use that resource which is somehow scarce or expensive, what have you, for only the parts that it provides some benefit. And so for that particular reason, we really see power in capabilities that allow you to locate a quantum resource within a larger compute framework, where it becomes easy to use it for that part of the task which it is good at and use other technologies where they make sense.
Okay, thank you.
Mm-hmm.
Yeah, can I take a picture of this?
Sure.
Yeah. Go ahead.
Anything else? Okay, thank you.